Hello everyone and welcome. Today I would like to talk about the question LRU cache. This question asks that you design a data structure that follows the constraint of a least recently used cache. The key phrase here is to design a data structure, which is a pretty big hint in this question. It means that you are not using an existing data structure, but rather you need to create a new data structure. Because of this, I rate it to be a hard question instead of a medium level question if you are not familiar with design a data structure before. Importantly, the question asks that you implement the functions get and put in O1 average time complexity, which can be a tough challenge here. So what exactly is a LRU cache? Well, basically, it's a queue structure, and you have a least recently used item here. An item is a key value pair. As a first item, you also have the most recently used item as the last item, and the maximum capacity is capped at the upper limit of a certain number. And so here, any key value pair touched by put or get will be placed at the end. So because they are recently used. And when overcapacity, if you add a new item, then the oldest item will be evicted. This table here gives you an example how this LRU cache should behave. But the middle column here also provides you the internal representation, how it will be working internally, and give you an idea of the proper mechanism. Based on the understanding of a LRU cache, you may be able to implement a brute force solution using list as a queue data structure. You can pause this video to see how it's implemented here. Based on this implementation, there are two thoughts. First, the time complexity is On since we iterate over the whole cache, and is larger than the O1 requirement. To achieve O1, we typically need a Hashmap. However, second, Hashmap is not older as you know. Thus, we need an older Hashmap. But how do we build a data structure as an older Hashmap? Well, how about we build a doubly linked list within a Hashmap? So Hashmap, as you know, is similar to a set. The element within the set is unordered, but different from a set, it has a key value pair. But if we are able to link the items, like which one is the previous item, which one is the next item, then we can actually establish an order among the items within the hash map. In another word, to solve this question, you need to combine two different data structures, a hash map and a doubly linked list. Then you can create a new data structure as an ordered hash map. With all the background understanding introduced, now let's try to write the code. But first of all, I would like to implement the brute force solution one more time and then improve from there. So for this class, we create a self capacity variable to keep track of the capacity, and for the cache, we use a list. And for each of these items, we use a tuple to store the items, the key value pair like this. So here are two tuple examples. And then for get function in this class, we basically iterate through the cache to see if we have a match. So we'll do a for loop through the length of this cell cache, and then if the tuple's first element is a key equal to the key, then we have a match. And then we want to return the tuple's second element, which is a value. But before that, since we touch this element, we want to move it to the end. So to move it to the end, we basically will append this element. So self cache, we append this particular element, and we also want to pop the previous place like this, and then finally we return the last one, which is the tail. Okay, and if this throughout this iteration we cannot find any match, means it is not in the cache, then we will return a -1. As for the put function, we want to update the value if already existing. So we iterate through the cache to find if there's already existing in the cache. So if the first element of the tuple equal to key, then we have a match here. And what do we do with the match? Well, actually, we can pop this particular item and then break the for loop, and then I'll just append the tuple as if we encounter it for the first time. So it's equivalently move to the end. And if there's no match, then we just add to the end. So this is working. But if the total length of this cache is now greater than the capacity, then we know we need to trim the least recently used item. So basically we'll pop the first one. And that's our brute force solution here. We can also test this solution to see how it works. So we submit, and it's judging. We'll expect some error since the question asks for the O1 time complexity, and this definitely is not O1 time complexity. So let's see. So there's no, so the code is working, but time limit exceeded. This is because there are two for loop here, and for each of these for loop, the time complexity is definitely for n. Okay, so now we know this is working, but the problem is the time complexity, and we want to use older hash map instead of this. So let's create a new class, call it the older hash map here. You inherit from the dictionary, and so we will call it a older hash map. Okay. So here, what are we going to do with this older hash map? So since it's a hash map, but how can it be ordered? We need also create another class known as a Doubly link node for the Doubly link list. And this one is pretty simple, so I'll implement this one first. Basically, it will store 4 variables in this class: key, value, next, and the previous node, where it's pointing to. So, and we initialize to be none here. Okay, so we have this doubly linked node class just implemented. Next, we're going to implement this order hashmap class. And how we're going to do that? So it will look like a dictionary with a key and a node, key 2 and a node. And the node has, as you can see here, 4 information. So next one, previous one, next 2, previous 2. So and so on and so forth. So this will be what it looked like for the order hash map. Okay, so now let's implement this ordered hash map. Okay, so we'll define the initialization function, and we will need 2 nodes, the head node as the empty link, doubly link node, and a tail node as empty doubly link node. And so now we want to try to think of everything in terms of nodes. Okay, so we're going to revisit the LRU cache to see how we can convert the understanding into node instead. So in the get function, instead of iteration, we'll see if the key is in the dictionary, right? Because this one will give us a time complexity of 1, and we don't need the equal function anymore. And so if the key is in the cache, then the value will certainly be and the node's value, okay. And then we want to return the value. But before we want to return the value, we will move this item or this node to the end of the ordered hash map. How do we do that? So we want to think of everything again in terms of node here. So we will basically change thing in terms of node. And then we will append a node and then pop the node, and we'll refer them by key. Just to avoid any accident, we want to pop it first before we append, so we don't accidentally pop the one we just appended. So we pop by the key, and we append by the key and its value. Okay, so let's implement this way. And here we'll add corresponding functions. So we pop node, and we also have another one called append node. Okay, and we will implement them later. Okay, so now let's visit the put method here in the LRU cache class. So again, we don't need to do the iteration anymore, since we can use a dictionary lookup. And this one has a time complexity of 1, importantly. And so if this element, sorry, this key is in the cache, and we want to pop it, so we will do the pop node, because we want everything in terms of node here, and we don't need a break since it's not a for loop. So we pop a node, and then we append a node. With key and value. So you can see here. So let's say if the key is not found, then we simply append a node. If the key is found, we remove that node and we append a node with the new value. So it should be working. And finally, we will have a pop 0 here. It means we want to pop the first node. So we'll implement like this. Okay, so we'll add another function called pop first node. So next, we will focus on implement this 3 function in the class ordered Hashmap. So how do we pop a node by the key? Well, we can consider, well, first of all, using the previous and next. And this is important. So that's how the doubly link list work. And in the head and tail, we'll also do the same thing first. So head next is tail, and tail's previous is head. And to pop a node, it basically means the node to pop would be self key, since self is a dictionary. And we want to connect the previous to next without this node to pop. So basically self key previous next should just point to self key next directly, and the self key next previous should also point to self key previous. So then now we don't need self key anymore, and we can pop the item. So that's how it works. After implement this pop node function, next we'll implement this append node function. For append node, the idea is that we'll create a node, a new node, and then append to the end. And so there's a tail, and so previously there's another node point to the tail. Now we want that another node point to the new node we just create. We're going to create, and the new node will point to the tail. So that's the idea. So first of all, we'll create that new node using the Doubly link node class with the key equal key and value equal value. Okay, so that handles the new node part. And second, we want to find the previous one before the tail. So the tail's previous now should point to the new node, and the new node previous should also point to this because it's a double link. So and then let's implement 3. And this 2. For 3, it's also the double link like this. So we already take care of the new node, and now how about the new node for the tail? So the key next should point to the tail, and the tail first should point to the new node, and that's it. There we implement append node function. And just to document this for completeness, double linkness. So the 2 previously is like this, and now it becomes like this. Okay, so next I'm going to implement the pop first node function. For pop, the first node, it's actually pretty simple because we can simply use the pop node function, and the key here is simply what the hex, the next point to. So that will work as a pop first node function. And now we actually have everything we need, so we are ready to test to see how it works. So let's submit it. Submit, pending, and judging, and it done. Let's see. So accepted. Faster than roughly 50% of Python online submission. It works pretty good. So here is the solution for this order hash map, and we can also analyze the complexity here. So it's used dictionary, so O1 time complexity, by the fact that it passed the evaluation, so it indeed O1 time complexity, and the order hash map using the double link list has this O1 lookup time, and for the space complexity, it will be the cache, since there may be up to the capacity here. So we know the total time complexity is O1, and the space complexity is ON, or capacity. And that's all. Thank you very much for watching. It's a relatively hard question. Hope you find this video to be useful, and please subscribe for more videos. Hope to see you next time. Goodbye.